Hi, my name is Steve Montgomery, creator of Whisker.io. In this tutorial, I'm going to show you how easy it is to build a wireless sensor network using Whisker.io, and we're going to do it without writing a single line of code. The Whisker.io engine is capable of serving as both a gateway and a sensor. A gateway can be as simple as a Whisker engine connected to a PC via USB port. Here, we have all the components we need. Building the gateway is simple. First, we connect the Whisker engine to a USB adapter, connect it to a PC via an extension cable, and connect our antenna. The Whisker engine is essentially a self-contained wireless sensor, requiring only a power source and antenna to function. And although the engine is capable of interfacing to many types of analog and digital devices, it comes with a built-in temperature sensor. Therefore, using just these few components, we can build a wireless temperature sensor in seconds. An important thing to note is that every Whisker.io device comes with a unique serial number or MAC address, which is clearly marked on the product label.
Okay, now we have a basic Whisker.io network setup. Using a simple terminal emulator, such as RealTerm, we can interact with the remote Whisker.io engine using AT commands. For the purposes of this tutorial, we're going to turn the remote engine into a battery-powered wireless temperature sensor that measures temperature and battery voltage every minute. To start, we need to set up RealTerm to make it easier to work with Whisker. So first, let's set the display to show 40 rows instead of 16. That'll give us more room to work with. Also, you'll notice I've got this set to half duplex. That'll allow my keystrokes to be shown in red so it's easier for you to see what I'm doing. We also need to configure the port. The port needs to be set up for 115.2 kilobaud. We need to select the proper port. Parity is none, data bits are 8, one stop bit, no hardware, no flow control at all. Make sure you hit change, and that should get it configured. Now that we have the port properly configured, we should be able to hit 3 pluses and put the local engine into command mode. And we know that it accepted the 3 pluses and went into command mode because of the OK response. Anytime you type a command that's properly formatted, you will get at least an OK response from the local module. If you type an improperly formatted command, you will get ER, which indicates that there was an error. As I said earlier, we want to configure the remote engine to become a wireless temperature sensor that reports temperature and battery voltage once every minute. So the first thing we need to do is configure our local engine so that it knows which remote engine to communicate with. And to do that, we set the target MAC address with the ATTM command. And you'll remember from earlier that every module comes with a MAC address. It's clearly marked on the top of the module, and all you have to do is type that MAC address after this command, and that will set the local engine so that it will communicate with the remote engine that you want. In this case, we want DE1A 0E8A. And that sets the target MAC address. Now that we have the target MAC address set, we actually need to communicate to the remote module, and the first thing we want to tell it is that our local module is the one that it should send all periodic notifications to. You can have the target MAC address for the local module set to any one of a number of remotes that are in the network, but all of the remotes need to know the MAC address of the local or the gateway or the master, whatever nomenclature you want to use, so that they know where to send the sensor data that they're collecting, and that's what the ATMA command does. Now you'll notice when we send the ATMA command, we actually get 2 responses. The first one is from the local module. The second one is from the remote module. RMOK tells us that it accepted the command and executed it. The C7 is the RSSI that the local module measured when it received the response from the remote module. If we had sent a command that was properly formatted but had an invalid channel number, for example, we would get RMER to indicate that there was something wrong. The end of every remote response that we get is going to have the last 2 characters with the as a hexadecimal representation of the RSSI value. Now we just need to configure the remote engine to periodically measure the internal temperature and battery voltage and report it once a minute. The ATAI command, whoops. So this is what happens when you enter an improperly formatted command. The commands need to be capitalized, and if you enter one that is improper, you'll get the ER response. We want to type ATAI capitalized. That's going to tell the remote module that we want to enable periodic or interval measurement on a particular channel. And in this case, we want channel 1D, which is channel 29 in decimal, and you can look in the data sheet and see that that represents internal temperature. And then we want to give it a parameter of 01 to indicate that we want that channel to be measured every sampling interval. If we wanted to disable that, once it's enabled, we could type ATAI 1D00, and that would take it out of periodic sampling. Hit enter. Again, we get two responses. But first, let's go ahead and set up the module for periodic sampling. So we're going to type ATAI 0301, and this is going to set up the channel 3 the same way we set up channel 29. Channel 3 is battery voltage. So with that done, now both of those battery voltage and temperature should report every sampling interval. All that's left to actually get samples to start coming to the local module from the remote module is to set the sampling rate itself. To do that, we use ATSR, and this is followed by an 8-digit hexadecimal number. It's a 32-bit number measured in 1 minute increments, so we're going to just do 1 minute in this case, so it's 7 zeros followed by a 1. Now there's no requirement that says that you can only periodically sample analog or digital channels. You can also get instantaneous sampling if you want, using a different set of commands. So if you wanted to know the channel value for channel 3 or channel 29 right now, we could use the ATRA command followed by the channel number, and that should give us a value. And the response is basically RMRA tells us that it's a response to the RA command. 1D is the channel, and 00F9 is the actual raw value. The last two characters are CB. Now you can see we've received a couple of the periodic update responses. There's a big difference between the RMRA response and the RMPU response. The RMRA is actually a response to a command, and it'll only ever be sent from the remote module when the command is sent by the local module. Because of that, we always know which remote module this response comes from. When we configure a remote module to periodically sample and send data, or even to send information based on events, we won't know the MAC address of the module that sent that update unless we include that in the message. And that's one reason that you'll see this RMPU message has a lot more information in it. These messages are automatically generated either based on events or periods. This message will always have 2 characters right after the PU, and this indicates the length of the message. And based on that, we can tell how many channels are being reported. An RMPU notification message can have up to 4 channels worth of data in it. Right after the 0C, you'll also notice some characters that are numbers that we should recognize. DE1A 0E8A is actually the MAC address of the module that sent this update. Following the MAC address, we actually have the channel data itself. Channels can either report a 16-bit or a 32-bit number, and that all depends on the channel type. In this case, the only channel types we're using are analog channel types, so the numbers are actually raw 16-bit values. 5D isn't a channel that we recognize, but it's pretty close to a channel we recognize because we set this up so that we would have channels 1D or 29 and 03 reporting. Well, you'll notice we have 5D and 43. That should give us a hint that there's a flag involved here. We actually take the upper 3 bits of this number and we use that to indicate what type of channel this particular channel is. And you can look in the data sheet to see how the flags work, but if it's ORed with a 40 hex, then that tells you that it's an analog channel. So here we have channel 1D. We have a raw value of 00FA, and if we convert FA to decimal, we get 250. The temperature channel is reported in fixed point as a fixed point number. Basically all you have to do is take the number you get and divide by 10, and that tells you what the temperature is in Celsius with 10th degree resolution. Likewise, we can come over here and look at the second channel, which is channel 3, and again you'll notice that it's been ORed with 40 hex, so that's how we know it's an analog channel 3. And our raw value here is 010B, and that is 267 in decimal. Now in this case we're actually going to divide it by 100 instead of 10 because we need 2 decimal places, and that gives us 2.67, and that's the actual battery voltage. So we've got a temperature of 25 degrees Celsius and a battery voltage of 2.67 volts, and then these last 2 digits as always are the RSSI. So it really is that simple to set up a wireless sensor network with Whisker.io. With just a few short AT commands, we were able to configure a remote Whisker engine to measure temperature and battery voltage and report that to our local gateway engine every minute. If you need technical support, we encourage you to use our forums. They are available by visiting our website and clicking support and forums, or you can go directly to forums.d6labs.com.